In this video, I'm going to explain how oil is processed and how it's used to form alkanes and alkenes. It starts off millions of years ago, when organic matter, such as plants or animals, dies and falls to the bottom of the ocean. Over time, this layer builds up until eventually the lowest layers of it begin to be crushed under the pressure of all of the matter above them. At this point, the organic matter starts to break down into oil, but because it's trapped under many layers of soil and rock above it, it cannot escape, and instead is just left in large pools under the sea. Skip forwards millions of years, and humans arrive. We know that there's oil under those layers of rock, but we can't access it, so we construct large platforms called oil rigs that are able to drill down below the layers of rock and collect the oil. At this point, we have the oil, but it's still in the form of crude oil. Crude oil is useless and requires refining until we can use it for anything practical. Crude oil is made up of many different compounds, but the ones that we're interested, and also the most common, are the alkanes. Alkanes consist of a chain of carbon atoms, each saturated with hydrogen. This means that every carbon will have 2 hydrogen, except for the end 2, which will have 3. Because they are made of carbon and hydrogen, they're called hydrocarbons. The general formula for identifying an alkane is CnH2n plus 2. This means that, for example, if an alkane had 4 carbon atoms, it would have 10 hydrogen atoms. One problem, though, is that we have a large mixture of different alkanes in our crude oil, so we need a way to separate them out. The technique used for this is called fractional distillation. In fractional distillation, the crude oil is heated up until it's a gas, and then it's released into a large container. The container is made up of many layers stacked on top of each other, each layer being maintained at a different temperature, going from around 350 degrees centigrade at the bottom to around 25 degrees centigrade at the top. This means that as the gas rises up the column, the different compounds will condense in different sections. By capturing the condensed compounds in each section, we're able to separate out the different alkanes. This only works because different alkanes have different boiling points. We're able to predict the boiling point of an alkane based off the length of its chain, as the longer chains require more energy to break them apart into a gas, and thus they condense lower down in the column. Now that we have all of our alkanes separated, we can put them to use. Longer chain alkanes are thicker, and thus often used for things such as road surfacing. The very short chains are in a gaseous form at room temperature, and are thus only really used as fuel. The alkanes in between have a range of different uses, ranging from petrol to jet fuel. Alkanes have a very simple naming scheme. They have a main part of the name, and then they're just suffixed with ane. For example, hexane would have 6 carbon, and decane would have 10. The only really confusing ones are the first 4, namely methane, ethane, propane, and butane. You can, however, remember these 4 using the mnemonic, my extremely painful boil. As larger alkanes are often less useful than shorter chain lengths, we can use a technique called cracking, not to be confused with fracking, to break down the chains. One form of cracking is by using a catalyst. The long alkane is vaporized and then passed over a catalyst. It then breaks down in a decomposition reaction into a shorter alkane and an alkene. That's enough for this video, but I'll be making a video about alkenes very soon, so do look out for that one.